Hi all, welcome back. And in this video, we are going to learn about segmented paging. So, in the last few videos, we have read about some of the non-contagious memory allocation techniques, among which we learned of paging, inverted paging, multi-level paging, and segmentation. But the problem with segmentation was that when we divide our entire program into different various size segments and they are brought from LAS to PAS, then we face the problem of something called something problem called external fragmentation, which is also same problem we faced in variable partitioning scheme, right? So this problem of external fragmentation comes because we are allocating variable size segments into the memory at certain memory locations. So we have this problem of external fragmentation. Now to eliminate this, okay, we need to eliminate this external fragmentation, and hence we apply again paging technique on segmentation. Now how we can apply paging on segmentation, that's why the topic is named as segmented paging, right? So now how we apply the paging on segmentation, that we are going to see in this lecture. Now let's say we have this LA being issued as 34 bits. Now from segmentation part, we know that this LA is a combination of segment number and corresponding process ID. Okay, so this is this LA is 34 bit, and this is a combination of segment number. And we just this is our search term for the segmented table, but this LA is a combination of S and D. So S is the segment number and D is the size or segment offset, okay, word offset of the segment, right? So this way the CPU generates the logical address. Now let's say we have a segment, okay, and this is our segment of size, let's say uh, 64 kilowatt. Okay, so whatever segment is the CPU requires, this is our required segment, which has a size of 64 kilowatt, and the CPU based upon the D we fetch the particular instruction. So if it is 64 kilowatt, so it is 0 1 2 so on up to we can say 2 raised to the power 16 minus 1, right? So in this way these word division are getting mapped. So if it is a segment of size 16 kilowords, so they are all together 2 raised to the power 16 rows into that, and in each row one word is there, right? So this way we divide each segment, and from D part, that is the segment offset, we fetch the particular word whatever which is required, and S denotes the segment number, which segment number we require. So in this way the process was ongoing. But now what happens that to eliminate external fragmentation, now we are dividing this entire segment into certain equal size pages. So what we are doing, we are applying paging onto the segment. So let's say we are dividing it into equal size pages. Okay, so we have divided it into, let's say, 1 kilowatt pages. So this is 1 kilowatt. Again we have divided it to in some 1 kilowatt pages. So this is 1 kilowatt, 1 kilowatt, and 1 kilowatt. So on one segment, we have divided it into 1 kilowatt pages. Now, how it becomes something like this. So now we have a page table, or let's say we have a table which consists of all the pages of the segment. So these are the all pages of segment, and these segments starts from 0, 1, 2, and so on up to 2 raised to the power. So, how many pages of 1 kilowatt it will be? Like it is 64 kilowatt. So we divide it by 64 kilowatt upon 1 kilowatt. So there are altogether 64 pages, 2 raised to the power 6 pages altogether. So here we have 2 raised to the power 6 minus 1 altogether pages. And each page is a page of the segment, right? Each page refers to the page of segment, right? Each page is 1 kiloword. So that's how we apply paging onto the segmentation, right? So we can find out the number of pages in a segment, and that is equal to the segment size. Now, segment size is nothing, you can just get it from the D component of the logical address and divided upon the page size. So the page size will be the number of pages in which we have divided. We can get it from here. So if we have the segment size of 64 kilowords and we have the page size of 1 kiloword, so total number of segment will be 64. So from here the paging concept comes into picture. So we are applying paging on each segment of the present in the LAS, right? So now and yeah, one more thing, segment size is coming from whenever the CPU generates the logical address S and D, so this D denotes the segment size. So this D actually denotes the bits to represent one segment. So 2 raised to the power D is the segment size. So here, from here you can get the whatever is the segment size, and page size will be given to you. Okay. So in this way we are applying paging on each segment. Now see what the scenario looks like when we apply paging. And one more thing, number of entries in the page table, number of entries in the page table of segment is equal to number of pages in a segment, right? This is an important part. Okay. Now let's see how do we do segmentation, and how we are dividing. So let's say earlier we have this LAS, and in this LAS we have the program stored in various variable size segments, right? So this is our LAS. Now here we have applied paging onto. So there are certain segments already present here. Now what we are doing, we are applying paging onto each segment. So we are dividing it into equal size spaces. So basically here it is a segment only, but we are applying paging onto this. We are dividing it into equal size pages. So 0, 1, 2, 3, 4, 5. Altogether 6 segment, because let's say if it is a 64 kiloword memory, 64 kiloword, if it is sizes, and we are dividing it into equal size okay, just a second. So this is a segment, right? And we are applying paging onto this segment. Okay, please remember this part. We are applying paging onto this segment. So this 64 kilowatts refers to this segment only, right? Don't confuse that we are dividing it into various segments. Just a second, give me one moment, I just have one call. uh, 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 Okay, so we were discussing about this LAS, and in this logical address space, we have various segments, right? So all these are segments, and for each segment, we are applying the paging, right? So for each segment, we are applying the paging. But from the user's point of view, if we say that this is the LAS, so for this LAS we have different segments. Let's say if let me redraw this diagram again so as to show the various segments of this. So let's say if we have the LAS and we have certain size of the LAS, and we have all our program stored in this LAS and into various segments. So let's say this is 256 kiloword LAS memory, and here we have all together all the segments being stored in this LAS. I'm sorry for this curvy line, it would be straight, but it's just an illustration, so bear with this. So this is this LAS, and here we have all these segments. So these are the segments being stored in the LAS, right? 0, 1, 2, so on up to 2 raised to the power 18 minus 1. So these are the segment number. Okay. Now each segment is equal to some kilobyte or what. So altogether, this illustrates the total number of segments in this LAS, right? Now again, we have this PAS, which is the physical address space, and here we are bringing some of these segments here, right? And we have here the frame number. So these are the frame number. Now let's assume it from the CPU point of view. So let's say the processor P generates a logical address. Now processor will be generating the logical address based which will comprise of the segment number S and D, right? So this is S and this is D. Now this is the segment number which segment the processor wants, and this is the segment offset. So within a segment which word processor needs, right? So this is based upon this logical access memory, but we don't have the segments to be brought from here. We have to bring it from here, right? So some address translation needs to happen. Now what will happen, let's say this logical address, this segment, this is 18 bit, of course, because the total number of segments here is 2 raised to the power 18, and let's say this is 16 bits, so the D is 16 bits, right? So altogether this is our logical address. Now we have this address translation table. So for each segment here, we will have the corresponding base address of the segment, right? So for each segment, let's say 0, 1, 2, and so on up to 2 raised to the power 18 minus 1. For each segment number, we have the corresponding base address x is the base address of the particular segment, and let's say L is the size of that particular segment. Okay, just like segmentation, it is happening. So for each segment, if there are altogether 2 to the power 18 segment in this LAS, so for each segment, we have the corresponding base address of the segment and the corresponding length of that, right? So when it generates this logical address, we will look into this particular line and find out which segment we does the CPU requires, and from there we will calculate the base address. Then we will compare the L part with the D part, and here is our comparator, and we will find whether D is less than L. If no, then it is a trap to OS. But if it is yes, then what we will do, we will take up the X part, the base address here, and we will add the D here, right? So we will add X plus D to find out what is the segment number, right? This happens in the segmentation part, right? Now here is something which is a little bit different in case of segmented paging. Since we have applied the paging on each segment, so X gives us the base address of segment and D gives us the offset of the segment, right? So what will happen here, so I'm just changing color to illustrate this. Let me first delete this. Okay, so now if it is a yes, D is less than L, then what will happen? We have this D. Now from this D, it gives us the word offset of the segment. X gives us the base address of the segment. X is the base address of the segment, right? Now here, what we will do, we will calculate from, we have divided segmentation on this D. So D part is nothing but a number of bits required to represent a segment. So always remember, in segmentation paging, we have applied paging on the segment. So if D is a 16 bit, right? So altogether we have total size of the segment as 2 raised to the power 16, and this has been divided into, let's say the page size of each segment is equal to 1 kiloword. So altogether we have 16 pages right? So for that 16 pages, we will be having one page table. Okay, so it is the page table for the segment, right? So we can write it as 0, 1, 2, so on up to 63, because if there are if the total size of the segment is 2 raised to the power 16, and 2 raised to the power 10 is the page size, so altogether 2 raised to the power 6 is the total number of pages in the page table of segment. Now here what will happen, that with this d, which is the 16 bit total bit, this will get splitted into this page table memory address consisting of P and D. Now this P gives us the page number of this particular segment, and D gives us the page offset where is our word is present. Okay, so this D gets changed into P and D, and from here we get the P as 6 bit, because altogether there are 64 pages. So from here we get into the page, which page we want to access, and D will give us the word offset of that particular segment. Okay, so this is the 10 bit. Now from here we are getting the word offset of this. Now what will happen, we this x gives us the base address, so this is the base address of this particular segment, and for this we have the table, right? And from this table we are getting the page, which page we need to access, and which d offset, I mean the word offset of the segment. And now what will happen, so from here we are getting the frame number. So now the frame number becomes the F and D. So from here D is equal to this one, and F is equal to the entry inside the page number. So I think it got a little bit let's enlarge this part. So let me enlarge this part. So we have this S and D part. Okay, so first thing happens, what we have, one address translation table. So for each segment, we have particular entry. Let's say we have X and L. So X gives us the base address of the segment, and L gives us the size. So first we compare that whether our D is less than L. If it is no, then it is a trap to OS. But if it is a yes, then we have something called D. This D, it got split into P1 and D1, or yeah, P1 and D1. So if D is, let's say, 16 bit, so we have from here we are getting this X, the base address of particular segment. Okay, base address of particular segment. Now we have the particular segment, and we get this particular segment, so we get the a page table for this particular segment. And in this page table, because here we are not just accessing this segment in terms of a big chunk, we are accessing it in the form of page table we are creating for this particular segment, right? So just a second, let me just clearly draw this. Right, so we have got this base address of this particular page table of that segment that we want to access, right? And here what will happen, that in this D part, which comprises of 16 bit, so 16 bit is the overall size of the segment. Okay, so we have applied paging on one segment. So if we apply paging on one segment, let's say the page size in which we divided is 1 kilowatt, so 10 bit will be used to represent the page size, and 6 bit used to represent the page number. So here this part is actually, this part is P1, that is the page number of the particular segment, and this part will give us the D part. So D part will be here, and this will definitely contain the frame number. Okay, so from this D we are getting the frame number, and from this D1 we are getting the offset, right? So P1 will give us the frame number, the entry will give us the frame number, and from D1 will give us the offset of that particular part, right? So in this way it gets divided. It will be clearer with the help of example we are going to see. So let's see some examples onto that, and then it will be much clearer from there. Okay. So before that, just let me illustrate some point. So to avoid the overhead of bringing to avoid the overhead of bringing larger size segment larger size segment into memory, segmented paging is introduced. And in segmented paging, paging is applied on each segment. Paging is applied on each segment, and instead of bringing the entire segment into the memory, pages of the segment are brought into the memory. Okay. So if we say if the CPU generates S and D logical address, so D will get split into P1 and D1, right? Now here P1 denotes number of bits required to represent pages of the segment, and it is also known as the page number of the segment. Page number of segment, right? Similarly, if we have the D1, so D1 is the number of bits required to represent page size of the segment, right? And it can also be known as the word number of the segment, word number of the segment, or page offset of the segment, page offset of segment, right? So these are some basic points. So with that, I'm just concluding this lecture, but in the next lecture we are going to learn about some of the common questions based upon segmentation paging, and then it will be getting more clarified based on that. Okay, till that, keep watching, and if you do have any questions or comment, please do post in the comment section. Thank you very much.